everyone. Welcome back to Senior Flexonics Pathways Division of seminars on expansion joints. Today we're going to be talking about restrained expansion joints. Now, in previous seminars, we talked about the longitudinal pressure thrust and the need to consider that in selecting an expansion joint. We've also talked about unrestrained expansion joints and the special anchoring and guiding requirements. The type of joints we're going to be talking about today are all restrained. That's where we put some sort of restraint across the bellows element to restrain the pressure thrust and eliminate it from consideration. However, when we do that, we also lose some sort of movement capability. And so the selection of the type of the joint is fairly complex depending on your application. Matter of fact, many years ago when I was working with Caesar and thinking about automating the expansion joint type selection, I sat down and drew out this logic flow chart. And this is just the tip of the iceberg, but you can see how complex the selection process is. Hopefully today we'll give you some data points for assisting you in selecting the type of joint. I might also suggest that if you're new to expansion joints and haven't seen the previous seminars, that you go to our website and download our catalog, which has a very good discussion of types of joints and when and where to apply them. And the most typical or common type of expansion joint, restrained expansion joint that we sell is the tied expansion joint. This is where we'll take a bellows element and put tie rods across the expansion joint to restrain the pressure thrust. And so the load is developed at the elbow, travels down the pipe in tension, and goes through the lugs into the tie rods, across to the lugs, back into the pipe, and cancels with an equal and opposite force on the other end, thus eliminating pressure thrust, pipes in tension, externally everything is fine. However, what we lose when we do this is those tie rods must always be in tension, which means that the expansion joint can no longer accept axial movement, only lateral movement. Okay. So you would want to place this joint perpendicular to the axis of your movement. Here we see a tied elbow-to-elbow expansion joint. This is a refurbishment where the customer has taken the expansion joint out of their system and sent it back to our shop for cleaning up and mounting of new bellows and other hardware. But you can see the tie rod end plates and the tie rods themselves. Here's a schematic that shows a tied universal and how the expansion joint is located perpendicular to the axis of movement so that it can deflect laterally. You'll also notice that we have guides near the joint because as the joint swings through its angle, it will slightly foreshorten or draw the pipes up and down. So we do have to have some flexibility around the expansion joint. And here we have a movie that shows a universal expansion joint flexing. The next type of expansion joint I want to talk about is a hinge joint. What we do with a hinge joint is we'll wrap a set of plates across the bellows and pin it in the center so that that expansion joint can only move in one plane. Now, therefore, the expansion joint will only angulate. It will not take axial, it will not take lateral, it will not take torsion, it will only angulate and then only in one plane. It's very unusual to have a single hinged expansion joint. About the only time I would use this is if I was doing a pipe stress analysis and I was very, very close to meeting my allowables, but I just needed a little bit of softening of the pipe system to get it under. And so once or twice in my career, I've used a single hinge joint. More commonly, we use 2 or even 3 hinges operating as a system. You can see in this other photo how 2 hinges will take lateral movement and they'll also take in-plane rotation. And here's an example of 2 hinges, and it has a very long tie bar that goes off to the elbow. The reason they're doing that is all of the thermal growth between the anchor points of the hinges is captured internally to the expansion joint and there is no external force or reaction as a result of the thermal growth in there. And sometimes it's used as a method for absorbing large amounts of thermal growth internally with no system reaction. But you can see the two hinged, two Bellows element with the pins in the system. And here we have diagrams of how the system moves. And so it's basically moving similar to a tied universal on the left diagram, where it's absorbing lateral movement. But on the right, we have now introduced a third expansion joint. And so we have what's now called an articulating system. And it operates kind of like your arm. If you can imagine one hinge, two hinge, three hinges, and you can take your fingers and move it any place in this plane. And so that's where the hinge would work. Now, if you try to move out of plane, the hinges will bind up and resist that movement. And so for this reason, the three-hinge system is a very powerful method for absorbing in-plane movements with very low reactions. You'll generally see them around rotating equipment or sensitive nozzles. And here's a movie of two hinges operating similar to a tied universal. And you might ask, why would I want to use hinge joints when I could use a tied universal joint? And the answer to that is the center spool. Hinge joints capture that center spool and will not let it vibrate or sag or move in wind or seismic conditions. And so if you have a very large, very heavy center spool, or that piece of pipe between the two hinges, and you need to capture it, then hinges are the way to go. If you have a small diameter, thin-walled center spool, then probably a tied universal is the way to go. And here we have a movie of three hinges absorbing movement in plane. The next type of expansion joint we'll talk about is the gimbal. The gimbal expansion joint is similar to a hinge joint in that it has hinge plates and pins, but what we do is we rotate a set of hinges 90 degrees and put a gimbaled ring in the center. This allows the expansion joint to move in plane, like a hinge joint, but then also out of plane. So the gimbal joint can take really any angulation period. It cannot take axial movement, it cannot take lateral movement, and it cannot take torsional movement. Only angulation in two axes. Similar to the hinge, it's very unusual to see a single gimbal in application. Here again, only when you might need to soften up just a little bit your line. More typical application is to use a gimbal in pairs. Okay, but you'll never see, or you shouldn't see, three gimbals because that's too much flexibility. And I'll talk a little bit about that in a moment. Here you see two figures on how to use gimbal expansion joints. The figure on the left has two gimbal joints, and you'll notice that the thermal growth is coming from two different axes. Well, the gimbals can take this movement by angulating in two different planes. On the right-hand side, you see two gimbals and a hinge. Here again, this forms an articulating system capable of absorbing movement in any direction. Now, here again, let's revert back to the arm, where this is the hinge and this is gimbal. Now recall that with the hinge joint, we could move in plane anywhere we wanted, but it would bind up if we tried to go out of plane. If we replace the two hinges with gimbals at these two joints, we can take the in plane, but then all of a sudden we can go out of plane. So in effect, you can take that pipe and go anywhere you want to go with the two gimbal hinge system. We do not recommend three gimbals, gimbal, because that's too much flexibility. When you do that, all of a sudden your piping system can do this and vibrate and become unstable. And so for that reason, we generally limit to two gimbals and a hinge. Next type of expansion joint I'm going to talk about is a pressure balanced elbow or T. Now what this is an expansion joint capable of taking lateral movement and axial movement while canceling pressure thrust. You can see that we've added a balancing bellows on the back side of your line. And so what's happening is the pressure thrust is actually developing on the left-hand side of the expansion joint on that blanking plate. The pressure thrust is then transmitted through the tie rods to the lug back into the shell and cancels with an equal and opposite pressure thrust on the other side of the line. And so in effect, we've isolated these elbows so that they can move axially as well as laterally. Okay, so it's a very good way of absorbing movement, somewhat more expensive than the tied universal or the hinge system, depending on the diameter and complexity. And so you'll see these also on rotating equipment or critical nozzles. Now, one area of special caution and concern is the balancing bellows. That cavity will tend to run cold. And so if you have a condensing media, you could start condensing and have corrosive problems in the balancing assembly. Also, if you have a large particulate load, fly ash or products, dust, that can accumulate. And for this reason, we generally like to place pressure balance elbows and T's with the bellows aligned vertically so that that balancing end is self-draining. Here we see an example of a pressure balanced elbow, where on the left is our balancing bellows and the line bellows are on the right. Now you'll notice 6 heavy pipe rods spanning from the bellows to the balancing end plate. And that is because this is a vacuum service expansion joint, and those tie rods are actually in compression. Also, all of the thermal growth over the span of those tie rods is captured internally with no resultant force on the external system, so we can capture a large amount of axial movement internally to the expansion joint. And here we have a movie demonstrating how a joint like this would be used around a turbine. Okay, the last type of joint I'm going to talk about is the expansion joint of what I call the expansion joint of last resort. It's an inline pressure balanced expansion joint. Now the reason I call it the expansion joint of last resort is that they generally are very stiff, don't have much movement capability, are expensive, and we do have some temperature, condensate, and material accumulation issues with the balancing bellows. However, what's happening here is, here's an example of the largest inline pressure balance joint we've ever made. This is a 144-inch diameter joint for a steam distribution line in Saudi Arabia. But coming back to how does this work, what happens is we'll take a normal universal expansion joint and then add this center expansion joint that's much larger. And actually what's happening is we'll size that third bellows element so the annular area between the line bellows and the balancing bellows is equal to the area of the line bellows. So that when the system is pressurized, you'll get a pressure thrust pushing in one direction, a pressure thrust pushing in the other direction on those center rings. Now the pressure thrust on the left will go into the lugs, across the tie rods, back into the shell, and cancel with the pressure thrust on the right side. The pressure thrust on the right ring will go through its tie rods and cancel with the pressure thrust on the left side. And so in effect, we've created a balancing pressure thrust for both sides, and the joint can move axially and a slight bit of lateral. Now we can put a fourth bellows in there to convert this to a universal pressure balance joint to allow it to take a lot more lateral movement. And here's a typical application. I mentioned that if you're using this joint, you should be between a hard place and a rock. And this is where an example of that situation, where you've got 2 rigid vessels, a straight pipe in between, and the pipe gets thermally hot. You've got no room for a bend or a dog leg, and the vessels can't take the pressure thrust, and so you might want to consider an inline pressure balance joint. Here we see a short movie of how an inline pressure balance expansion joint would operate. And you can see the left side's growing, right side's growing, and it compresses the line bellows and extends the balancing bellows. And that concludes our series on types of restrained expansion joints. Again, if you want additional information or reading, I would encourage you to download our catalog. It has a really good discussion. Also, the Expansion Joint Manufacturers Association, EJMA, publishes a standard that you can purchase that also has a very good discussion on applications and types and when to use restrained expansion joints. So I hope you've enjoyed our little seminar today, and I look forward to seeing you at our next one. Thank you very much, and goodbye.